Okay, so before you watch the video, I want you to very carefully read through section 2, look carefully at the graphs that they give you, work through the problems. This is more of a summary of what you're seeing in section 2 than anything else. Okay, so what Ben talks about in this chapter is that, and it's kind of mind-blowing, but we can mimic many functions, such as sine and cosine curves, using polynomials, which is completely insane. Okay, what Ben does in terms of choosing and guessing coefficients on his polynomials is a little nuts, and I'm going to show you how to actually get those polynomials specifically to mimic sine and cosine curves. But the fact that I can get a sine curve using a polynomial is insane. One of the things that we're going to focus on is that these polynomials, I'm going to say that they kiss the functions they mimic at the initial point of tangency, which we're going to call the center, okay? And just like when we were talking about linear approximation, a tangent line to a curve touches the curve and is exactly the same as the curve at the point of tangency. The polynomial is going to branch out from that initial point of tangency, and it's going to hug the function it's mimicking from that it's a kiss and a hug. I know it's a little silly, but from that point of tangent, from that center. Okay, I say that it has equal arms. Okay, meaning that if this is my kiss, okay, then I'm going to hug equidistant from both sides of that. Okay, so I can reach out this far on this side and the same distance on the other side. It's never going to be, it's never a bro hug, so it's never a long distance on one side and a short distance on the other, or, you know, it's always equidistant on both sides, okay? So, in any case. Okay, so a Taylor polynomial or Taylor series. Now Ben talks strictly about polynomials to begin with, and then he brings in series later on. We're going to talk about them simultaneously because it's kind of silly. Okay, a polynomial just has a finite number of terms, whereas a Taylor series is going to have an infinite number of terms. The big difference is the plus ... at the end. Okay, so a Taylor polynomial or a series is centered or kisses at any point. Okay, the polynomial has a finite number of terms, the series has infinitely many terms. A Maclauren polynomial, the only difference about a Maclauren polynomial or a Maclauren series is that it has to kiss at 0. The center has to be at 0. Okay, again, polynomial finite terms, series infinitely many terms. It's just like saying that a square is a special type of rectangle. Maclauren polynomial is a type of Taylor polynomial. Okay, so you'll see AP will use two different ways to call a Maclauren polynomial. Sometimes they'll say a Taylor polynomial centered at 0, or sometimes they'll say a Maclauren polynomial. I could say a rectangle with all sides equal, or I could say a square. It's the exact same situation. Okay, so just to sum up what Ben talks about in section 2, Taylor polynomials, and I took this directly from his packet, Taylor polynomials match the function being modeled perfectly at the center. They lose accuracy the further you move away from the center, but they gain accuracy the more terms that you add. Okay? And again, it's weird how Ben was just picking random coefficients. So when you were thinking it was weird that Ben was picking random numbers and guessing and choosing and saying this was good and this wasn't. But there is a concrete way to come up with those numbers. He had some guidelines when he was choosing those numbers. Okay, so one of the things that Ben showed you is that we can take derivatives to get from one Taylor polynomial to another, just like we can take a derivative to get from one function to another. So because the derivative of sine is cosine, okay, we can similarly say that the derivative of the series that we're using to approximate sine is going to get us the series to approximate cosine. Okay, so the series that Ben came up with for sine was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Now Ben very nicely illustrated for you guys how those polynomials look, and how as you add more terms, the closer it's going to follow the sine curve, and the longer it's going to hug the sine curve from either side of 0, which is where it's centered or kissing. Okay, but so if I take the derivative of my sine, or the polynomial or series that's emulating the sine curve, I'm going to get the polynomial or series that's emulating my cosine curve. Okay, it is important for you to know these two polynomials or two series. Okay, you need to have the series for sine and the series for cosine memorized for the AP exam. So let's just make a note of those. Okay, so our sine series is just like the sine curve. It's odd, okay, meaning all the exponents are odd. So I have an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. My sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Again, I'm going to show you guys how to get these actual series, but Ben got it by lucky guessing, we'll call it, or it was guided guessing. And then our cosine series is even, just like the cosine curve is an evenly symmetric function. And that's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so on. Or the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. Okay, so it's important to know those two series. It's also important to realize that we can take the derivative of polynomials just like we take the derivative of functions. Okay, or series. It doesn't have to be a polynomial. Okay, we can make new polynomials for composite functions using properties of composites. Okay, so knowing what the the Maclauren polynomial, and these are Maclauren polynomials because they're centered at 0. The Maclauren polynomial is for cosine. I can make a Maclauren polynomial for cosine of x squared. So the Maclauren polynomial for cosine of x looks like this. And I just said Maclauren polynomial. This is the Maclauren series for cosine x, and the big difference being the fact that I have this plus dot dot dot, okay, and the fact that my series goes from 0 to infinity. Okay, now I actually am going from 0 to infinity. But if I want the Maclauren polynomial for cosine of x squared, I'm just going to make that composition the same way that I would make a composition with any other two functions. So if I have cosine of pi, I plug in pi everywhere for an x. Now I'm doing cosine of x squared. I'm going to replace all my x's with x squareds. So that would look like this. And you might want to pause and try to substitute all your x's with x squareds, and just until you get an 8th degree polynomial, which actually means that we should really have a similar to symbol here, okay? And I don't know why my program won't give me a true similar to symbol. I'd prefer to see something that looks like, well, kind of like that, just not so sloppy, but you guys get what I'm talking about. So this is going to be an approximation because I'm just going to do a polynomial. Polynomials approximate versus series give me true values because the series have infinitely many terms. That's something to stew about, okay? The fact that a polynomial is only going to be an approximation, whereas a series will get me a true value. Okay, so I'm going to make that substitution, putting my x squareds in place of my x's. I'm only going to do my first 3 terms here because I want an 8th degree polynomial, and an 8th degree polynomial is going to end with an x to the 8th term. And if I do x squared to the 4th, I'll have an x to the 8th term. I'm going to simplify this and have this, 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial. Okay, so we can make new polynomials very easily from what we know. This was one of Newton's absolutely favorite things to do, to use a Taylor polynomial to evaluate limits or to take derivatives or things like that. So in AB, we may or may not have told you to memorize this limit. It's in your AB textbook as something that you should just memorize in section 2.1, I want to say, when we introduce limits. And the idea of having to memorize a value to a limit like this is just ridiculous to me. Now we can use L'Hopital's because we get 0 over 0, but Newton thought it was just fabulous that you can use a Taylor polynomial or a Taylor series to get the limit as well, okay? And so we're going to take the fact of what we know about sine x as its Taylor series, okay? And sine x is my odd series. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And I can take the limit as x approaches 0 of those terms divided by x. Okay, Okay, so I know it says to use a Taylor polynomial. I'm going to use a Taylor series. I'm taking the limit as x approaches 0 of my Taylor series for sine. So x minus x cubed over 3 factorial plus x to the 5 factorial and so on, all over x. And I'm going to divide every term by x. So I'm going to do x divided by x, which is going to give me 1, and then x cubed divided by x, which is going to give me an x squared, and an x to the 5th divided by x, which is going to give me x to the 4th, and so on. So this limit would really look like this. And maybe pause and see what the limit actually looks like and see if you can evaluate it for me, and then come back. Okay, so I'm going to have the limit as x approaches 0 of 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial and so on. If I let x go towards 0, I'll have 1 minus 0 plus 0 minus 0 plus 0 infinitely many times of minus 0 plus 0, which is just going to give me a value of 1. Okay, so just another way, like I said, this was asked for you guys to memorize in AB. You can use L'Hopital's, but here I can use a Taylor series to evaluate this limit, which is pretty neat. Okay, so I can do composites. I could take limits. I can also make new series. If I want a Maclauren series for f of x equals x times sine of x, I can take my series for sine of x, and I can very simply multiply in another x. So I can multiply everything. I'm going to multiply x times sine of x, and I can multiply every term in my series by an x as well. So go ahead and pause and try to give me the new series for sine. Or, I'm sorry, not for sine, but for x times sine of x. Okay, so we're just literally going to multiply through by an x, and that will give me this new series. Okay? Another example. Okay, and I'm going to let you guys do this one. We just did cosine of x squared in, I think, our first example, and you can multiply through an x now and see what that looks like, and I will just come back to you with an answer. Okay, like I said, cosine of x squared we got before looks like this, and if I multiply in an x, I will get... Okay, so this is what it looked like. So multiply in by an x, and I end up with x minus x to the 5th over 2 factorial plus x to the 9th over 4 factorial, and so on. Let's look at something we talked about with just our geometric series, which is the series for 1 over 1 minus x. Okay. Again, if we look at this as the general form for geometric series, which was a over 1 minus r, or the sum of a geometric series, which was a over 1 minus r. Okay, and the fact that a over 1 minus r is the sum of a series where a is my first term and r is my general term, then this would give me, well, if a is my first term and r is my general term, then for 1 over 1 minus x, a would be 1. Okay, so a would be 1, r would be x. Sorry for the barking dogs, but a being the first term, and then r being the ratio between terms, I'd have a plus ar squared, and so on. And so if I combine that with a being 1 and r being x, I have the series 1 plus x squared plus x cubed, and so on. Okay, so we're going to take this whole idea and expand it to some examples. Okay, so looking at this from the... Oh, you know what? I don't think this made it onto the back of your outline. I think I forgot that this was there. So pause, write down the problems. We're going to find third order Taylor polynomials for the following function. So I have f of x equals 3 over 1 minus 2x. And what you're going to do is you're going to look at these as a over 1 minus r. Okay, so starting with this first one, if I have a on top and it's 1 minus r, then in this case a is 3. Okay, and then if I put that together with a being the first term and r being the ratio between terms, my third degree Taylor polynomial would come from this. Okay, so I'd take my 3, and then for my first term, and then for my second term I'd multiply that 3 by 2x. And then to get from my second term to my third term, I multiply in another 2x, so I get 3 times 2x quantity squared, and then multiply in another 2x, so 3 times 2x quantity cubed, and I stop after that fourth term because I asked for a third degree polynomial. We'll talk about the difference between an order and a degree in class, but it stops at an x cubed, okay? In the interest of time, I'm not going to simplify this, but go ahead and simplify this to distribute those exponents and so on. Okay, let's try B. Actually, in the interest of time, I'm not going to try B. I'm going to let you do B and you do C. Okay, it's very important that when you're doing these that you let it be A over 1 minus R, and we're going to talk about these together on Monday.